welcome to this special Earth Week webinar about climate change and Panama with Dr. Steve Paton. Before we begin, I'd like to remind you that the duration of Mr. Paton's presentation is about 45 minutes, followed by a question and answer period. Presentation, be sure to add your questions. Hold on, I'm going to turn my video on. Hi, here I am. Sorry, I was told to turn that off and nobody told me to turn it back on again, but here I am. So during the presentation, be sure to add your questions and vote for other people's questions on the Pigeonhole platform. Go to www.pigeonhole.at and type in the code CLIMATE. We won't have time for all the questions, so be sure to vote, and we will be sure to read the questions with the most votes. My colleague Elizabeth will read them for you after Dr. Paton's presentation. I would also like to remind you that the presentation will be recorded and available to the wider community afterwards. You'll be receiving an email with the link to access the video. So if you don't know me, my name is Nikki Barrett, and I'm the STEM and Sustainability Coordinator at ISP, as well as the mother of 2 current ISP high school students and 1 alumni. I got my master's degree in climate modeling before I did my PhD in ecosystem restoration. So I'm super enthusiastic about environmental science. I've been working here at ISP for 4 years to bring science and sustainability more into the consciousness of our school. I'm very excited about this parent initiative to bring in guest speakers to our community to further enhance our work together. A very special thank you to Babs of Airhoven and Donna Conlon, as well as our director, Vicki Steibert, who made this webinar possible for our community. Now I would like to introduce Steve Paton. Steve is the director of the Physical Monitoring Program at the Smithsonian Tropical Research Institute here in Panama. Mr. Paton has a bachelor's degree in biology from McMaster University and a master's degree from the University of British Columbia. He's been working here at STRI for over 30 years. In various areas such as data management, photography, biodiversity, and environmental monitoring. Since 2006, Mr. Paton has been the director of the Physical Monitoring Program, and he has been responsible for the long-term collection of climate, hydrology, and physical oceanography data to support the Smithsonian scientific mission here in Panama. The data collected by this program has been used in hundreds of national and international scientific publications. Due to his extensive experience, he is a renowned science communicator. In the last 3 years, he has presented dozens of talks on biodiversity, meteorology, and climate change at the national and international level, in addition to representing the Smithsonian at official meetings and conferences on the same topics. So whenever you're ready, Mr. Paton, please tell us all about climate change in Panama.
Okay, let me start. Climate change, share. Okay, welcome everybody. Thank you for joining me. I'm glad that everyone could attend, especially all you ISP students. I know that there's a lot of interest in this topic, and I'm glad to be able to share what I know about it. Now, before I start talking about climate change, I want to talk a little bit about science communication and what it is to look for information about a topic and decide whether the information you're finding is actually what you really want. Now, the difficulty of knowing what to believe when you're searching on the internet is a combination of factors. First of all, it's a failure of many scientists to communicate well. Many scientists, well, actually, part of our training as scientists is learning how to communicate your science to other scientists. But very few scientists learn how to communicate to non-scientists. It's a real specialty. And because that so few scientists do that well, there's a barrier of communication between scientists and non-scientists. The next problem is reality is really complicated. People like things to be really simple, that A plus B equals C. Well, it turns out it's A plus B minus D multiplied by X gives you sometimes Z. And it's really difficult to communicate that complexity when people are looking for really simple answers. The next problem we have is biases and sensationalism in the media. A lot of the media, almost most of the media, is a business, and businesses know that they really need to get and capture the attention of the audience, and the way they do that is by biasing their information, making things really sensational. They take something that's really small and they blow it up, and it makes it much harder for scientists to get in their message when they're faced with this media bias. The next problem is that we're so used to the 30-second soundbite. News organizations very often will give information about something really complicated in 1 or 2 minutes. Or if you're tweeting, you've got this curse of the 228 character. You have to fit in information into really small capsules. And now we've gotten used to that. And it's really hard to convey information about science when everyone's looking for these small little chunks of information. And the final barrier, and perhaps the worst, is this whole concept of fake news. Now, we all know what fake news is, at least in general. What we don't realize is that how pervasive it is. That the internet, the social media are absolutely full of fake information. Information that's fake either on purpose or fake just because people don't know what they're talking about. There are many businesses, even governments, that for political or economic reasons produce an incredible amount of outright lies and distortions of the truth. The fake news, it sounds reasonable. I mean, that's one of the reasons how fake news becomes so pervasive and so popular, because it's often made to sound really reasonable. It's usually encapsulated in those small little packets of information that people are looking for. Another problem is that as human beings, we're all susceptible to, if you repeat a falsehood often enough, it becomes a truth. Everyone believes strongly in a whole bunch of things that we've heard since children. But when you go and investigate, it turns out that a lot of them simply aren't true. But because we've heard it so often, it's the truth. And now, in the last 10 years or so, we're faced with the automation of fake news. There are now computers that produce literally hundreds of millions of fake news capsules, putting it out every day. And it's incredibly hard to compete against something that's become automated to that level. Types of fake news, different ways you can recognize fake news. First is the use of experts who lack the training in the subject. You very often hear a Dr. so-and-so talking about some subject, but when you look at what doctorate he or she may have, turns out it's completely unrelated to the theme. Use of researchers with financial motives. The best practices in science says that if you receive money for a company, anytime that you present about that information, and most assuredly when you publish on that information, you have to very clearly state where you got your money from. And very often people hide that. And so it's not obvious that people's information may be biased because they've gotten financing from a company. Another trick is to use information out of context. They very often will take part of something that a scientist says and put it in a completely different context so that it gives a 180 spin on what the scientist may actually have been saying. And then fake information is created with the intention of deception or just to create uncertainty. It's become very often obvious that certain governments have gotten to the point where they want to sow uncertainty in different societies, and they'll take fake news from both spectrums of the political ideologies, and they'll just throw it out, just throw doubt and confusion, and more than anything else, to lower people's faith in science and scientific communication. Now, my favorite example of this is tobacco. In the 1950s, tobacco companies already knew that the product was dangerous. But in order to protect their business, What did they do? They started to create doubt about the science. They started personally attacking the scientists. They overtly lied and created misinformation. And they spent billions of dollars to hide the truth. But eventually, decades longer than it should have been, the information finally came out, became so pervasive that people began to accept the truth. But it was something that was totally unnecessary. Hundreds of thousands of people lost their lives needlessly because of fake news. Now, why all this prologue? Because, in my opinion, exactly the same thing that happened with tobacco is happening with climate change. There are many people and businesses, for political and economic motives, are trying to hide the truth about what's really going on. They've taken the playbook used by big tobacco, updated it a little bit, and using it to deny climate change. And now scientists have this difficult task of explaining the science for all the different reasons I've explained. So as I'm going through this talk about climate change, I want you to keep in mind all these things I've told you, but I want you to hold me to the same level of providing information and providing certainty and showing why my hypothesis about climate change is true. Now, the Earth. The Earth is composed of a number of different important components. It's biodiversity, it's the oceans, it's the atmosphere, it's organisms, and it's also, to a great degree, you and me. But something has happened in the last 100 years to upset what was a wonderful balance that went on for tens of thousands of years between humans and the environment. And that thing is called climate change. Now, what is climate change? In the most general terms, it's simply a change in the long-term patterns of climate. But today, when we're talking about climate change, we're talking about changes that are consequences of human activity. And specifically, we're talking about global warming due to the accumulation of greenhouse gases. So that's what we're really talking about when we're talking about climate change. Now, we talk about the accumulation of these greenhouse gases, but what is this greenhouse effect? And greenhouse effect really is completely analogous to a greenhouse. A greenhouse, let me just get to my little pointer. A greenhouse has a shield made out of plastic or glass, and that shield is transparent to light coming from the sun. So the sun comes straight through it, and I'll get rid of my pointer, I guess. Okay, there we go. So the sun goes through that, gets absorbed by the plants, and it gets re-emitted in infrared spectrum that's called infrared. And that infrared really is heat. And that heat gets trapped, at least partially, by the glass or the plastic. And the more effective that plastic is, the more heat gets trapped. That's the greenhouse effect. Now, what we have on Earth is exactly analogous. Instead of plastic or glass, we have an accumulation in the atmosphere of greenhouse gases, primarily CO2, methane, a few nitric oxide gases. And these gases are transparent to the light coming from the sun. So the light gets through, a bit of it's reflected by the clouds, but a lot of it gets through to the Earth, and it's absorbed by the land and primarily by the oceans. And then that energy is re-emitted in infrared waves, and the greenhouse gases reflect back some of that infrared radiation, allowing accumulation of heat. Now, this is just physics. Okay, the physics is the more greenhouse gases, the more infrared solar radiation is going to be trapped, the more the temperature is going up. If you deny climate change, what you have to do is deny virtually everything we understand about the physics of the planet. You can't have both. You can't deny climate change and accept that we understand the physics of the planet, the two go hand to hand. Well, everything we understand about the planet, about the climate, about how the air and the water work, all says the same thing. More greenhouse gas, more the planet's going to heat up. Now, where do these gases come from? They come primarily from the burning of carbon and petroleum. It comes from land use change, primarily the burning of forests. This, by the way, is from Panama, the Bay of Panama, taken a couple of years ago. It comes from the melting of permafrost, primarily in Canada and Russia. It comes from rice agriculture, particularly the wet rice cultivation. It turns out that the water that's standing here is an ideal habitat for methane-producing bacteria. It also comes from cattle. The cattle are tremendous producers of methane, but they're also responsible for a huge amount of the burning of tropical rainforests. And it also comes from things like the production of cement and steel. Those two alone are responsible for over 13% of all the CO2 produced in the world. Now here we have a pie chart showing how it's divided in terms of types of different greenhouse gases. The most important is carbon dioxide, then you've got methane, nitrous oxide, and carbon monoxide from forests. What different aspects of our society are responsible? Heating and electricity, agriculture, transportation, industry, other buildings. Everything we do basically in our society, in one way or another, is producing greenhouse gases. How do we know these greenhouse gases, CO2 especially, is increasing? Well, there was a scientist by the name of Keeling in the 1950s began to notice in his laboratory that the amount of CO2 he was measuring was going up. And at that time, everyone thought it was completely stable. Now, it was in a laboratory, in a city, so it could have been just an accumulation of gases because of the development of the city. So in order to have a really good idea of what was going on, he established a laboratory on the top of one of the mountains in Hawaii. That way it was completely far away from any city, any major source of carbon dioxide. It was also in the middle of the Pacific Ocean, so it was going to be really representative of what was going on in the whole world, and he began to measure it every day. And the graph you see in front of you right now is called the Keeling curve, and it shows quite clearly that not only is CO2 increasing, that the rate of increase is increasing. So carbon dioxide is increasing. And we also know now that the levels that we're seeing, over 400 parts per million, are levels that haven't been seen on this planet for at least 3 million years. Now to give a bit more perspective, taking the levels of CO2 back 200 years, you can see how for many, many years, pretty much the entire history of human society, CO2 was constant. But at the beginning of the industrialized age, it begins to increase very slowly. But it wasn't until the end of the Second World War and the really tremendous industrialization of the planet that it began to take off. So that's where we are right now. Who's responsible for all this CO2? China is the #1 producer. It got ahead of the US about 10 years ago. It's US, there's the European community as a bloc, India, just because of the number of people in India, Russia, Japan, and Canada, the big developed nations of the world. Globally, you can see that and this is now, the graph before was on a country-by-country basis. Now we're looking at a country-by-country basis, but on an individual basis, because the production of a country just might be large, because in case of India, because there's so many people. But when you take a look at the production per person, you see that it's really the industrialized nations. India falls out completely. And it's these northern countries, highly industrialized countries, that are really responsible for the production of CO2. There are a few other countries that are major producers of petroleum that are also major contributors. What are the effects of all this CO2 in the atmosphere. The direct effects are obviously rising air and ocean temperatures. But we're also seeing an increase in the frequency of extreme climate events, storms and droughts, for example. We're seeing an accelerated melting of the permafrost, an even greater acceleration of the melting of glaciers and polar ice caps. The CO2 in the air and the water is going up. That's the primary motivator of everything. Sea level rise is undeniably going up. The oceans are acidifying, and there may even be the alteration of ocean currents. And that's one of the things that has scientists really, really worried. Now, indirect effects, effects that come from the previous list. We can expect in the future an increase in extreme famines, and the poster child for this will be Africa. There'll be a loss of life and property because of these greater storms. There's going to be a loss of biodiversity, especially in areas that are tropical countries like Panama. There'll be losses of sources of fresh waters. Those glaciers that are disappearing. It's estimated that right now, over 300 million people depend, at least during part of the year, on water that comes from glaciers. What are these people going to do when their glacier is no longer there? There are several major cities in South America, for example, in the Andes, that when those glaciers disappear, they're going to have real problems. Coastal erosion is going to be an ever-increasing problem, and it's already begun in Panama. There will be events of mass economic migration. If Europe thinks it's got a problem right now with a few tens of thousands of people going from Africa into Europe, what are they going to do when you get to an event of such extreme drought that it just exceeds any capacity to deal with? Instead of tens of thousands, Europe's going to have to deal with hundreds of thousands or even millions of people. There's going to be changes in agriculture. We're going to have to change the types of crops. We're going to have to change the way we're growing crops. There's going to be loss of productivity in many areas. There's going to be an introduction of diseases, and this has already begun. In Canada, for example, for first time that people know of, the Aegyptis mosquito has been trapped. It didn't carry up at the particular individual mosquito that they caught, didn't have any diseases, but it is a big red flag for the future of countries in the north that long thought they were immune to tropical diseases. North America has lost tens of thousands of hectares of forest because an insect, which used to be, its numbers used to be suppressed during winter. There were a number of really mild winters. The insect escaped that biological control, and it has wiped out tens of thousands of hectares of forest. These are the sort of things that we can expect more and more frequently in the future. Now, who is going to be most affected by these changes? And that's, we use the word vulnerability. Vulnerability has two different aspects. It's the degree of impact, but it's also the capacity of society to deal with those impacts. It's one thing for a big hurricane to hit the United States in a couple of years. It's all repaired, everything's fine. What is Bermuda going to do? The country, in the northern part of the country was pretty much leveled, and there are doubts whether they're ever going to be able to rebuild because they just don't have the capacity, the economic capacity to deal with that level of disaster. There are places in Honduras and Nicaragua that are still recovering from a hurricane that happened over 10 years ago. So these countries not only are going to be more impacted, they have less capacity to deal with those impacts. Now here, overlaid, the countries most responsible for the impact and the countries most likely to be affected. And it's just kind of odd that the countries most responsible for the problem are those least likely to be severely impacted. And this is really the crux of all of these international negotiations between countries that feel they're going to be it can be expected to be most impacted and the countries most responsible. The countries most likely to be impacted want the countries most responsible to pick up some of the bill. And these countries are a little bit hesitant to pay out the enormous sums of monies that are going to be required to deal with these impacts. That's why these international conferences often end in either no agreement or a watered down agreement. It's that real crux between people being most affected and people most responsible. Here's a graph grouping the different types of effects in 4 different major categories. And we can see here that Panama is in the crux of 2, almost 3 of those impacts. So Panama in no way is going to escape the severe effects of climate change. Now, remember what I said? I want you to hold me to the same level that I'm holding everyone else about fake news. So maybe everything I'm saying is just fake news. That's what certain politicians in other countries would like to say, that those people trying to promote the importance of climate change, it's just another form of fake news. So here's my evidence. First, we can begin with the fact that 98% of atmospheric and climate scientists say yes, that the phenomenon exists and that humans are almost exclusively responsible. Now, if you guys knew scientists, like I know scientists, finding a consensus at 98% on anything is almost a miracle. And it turns out these 2% that don't say yes are actually not saying no. They're mostly saying the evidence is still equivocal, that we need more evidence to be able to say yes. But almost nobody is saying that it's not happening, at least among those scientists who actually study this phenomenon. Now, yes, there are disagreements among scientists about the details, about the magnitude of the effect, the importance of some variables, exactly how things are going to play out in the future. And climate deniers like to play that as, okay, the science is really immature because the scientists can't agree. But this is really part of the scientific process. There are always disagreement about details. That's how scientists work, get closer and closer to the truth. But it's not the same thing as saying that the science is immature, that the scientists don't agree whether climate change is real. No, that's not true at all. Scientists thoroughly believe that it's real. It's just they're not sure about a lot of these details. Now, there's lots of evidence. There's direct evidence, temperature, sea level, greenhouse gases. I've already shown you that graph. Climate reconstructions from glaciers, coral, sediment, trees, all tell the same story, that the levels of CO2 that we're seeing now have never been seen for millions of years, that the temperatures we're seeing now are higher than has been seen in hundreds of years, possibly thousands of years, and most importantly, the rate of increase has never been seen before. There are even indirect observations. The Japanese have this wonderful 5-century-long history of the first flowering of the cherry blossoms. There are histories of thawing dates, retreats of glaciers, and they all paint the same picture. Something is changing in the climate, and it's all related to temperatures getting higher. And finally, the last real evidence that the scientists have are their computer models, these mathematical models. These same models that have allowed scientists, meteorologists, to go from predicting the weather only 2 days in advance to now 7 days in advance, to be able to predict hurricanes even 10 days in advance. It's the same math, the same models being used to predict the climate. And again, you can't deny climate change without saying that everything we understand about climate, about physics, about chemistry, about almost everything, because all of that information leads to the same end goal or end story. The climate is changing. It's changing because of increasing amount of greenhouse gases, and we're responsible. This is more or less one of the most official graphs showing climate or temperature change. You can see that there's a lot of variation year to year, that for many years prior to the beginning of the 1900s, the climate was stable. But then here we go, this era of the Industrial Revolution begins to change a little bit. And here we have post-Second World War, the massive industrialization of the planet. and temperatures take off. Those are the data. Those data can't be denied because they're come from multiple sources, multiple satellites, multiple ground-based data, and it all comes out and says the same thing. We know that the last 5 years have been the warmest on record. We know that the 1918 La Nina event was the warmest La Nina event ever seen. And La Nina events typically lower temperatures worldwide, and instead it increased temperatures. 2019 was the second warmest year ever. 2016 was the warmest year. So we've got these 5 years, including a La Nina event, that have been the warmest ever recorded in modern times. Now, yes, there have been changes in climate in the past. There have been periods millions of years ago when temperatures rose even up to 5 degrees Celsius higher than they are right now. But these events occurred over thousands of years. And that's the real issue here, that the environment, given enough time, can evolve with the changes. Given thousands of years, biological systems can adapt, can change. But what we're seeing right now is a change that's happening in a scale of decades rather than thousands of years. And this rate of change is absolutely unprecedented. And ecosystems simply don't have the capacity to evolve, to adapt fast enough. And the final nail in the story is, in the coffin, is that there are many data sets showing that there's a very tight association between the levels of CO2 and temperatures. And here we have, here's a graph. These are temperature and CO2 reconstructions from glacier ice cores going back 450,000 years. The red-blue line are global temperatures. The green line is CO2. And you can see that every time CO2 levels are low, temperatures are low. When they go up, temperatures go up. It's repeated 5 times in the last 450,000 years. And here we are today. This graph now should be up here. And the temperatures, based on this history, are going to come up. There's always a lag, and the temperature, because the Earth is so large, there's always a lag in between when CO2 goes up and temperatures go up. But it's a lag of a few decades, and that's too small to appear here. But the temperatures are going to follow this curve. That's the physics. Now, if all this wasn't enough, this is a really famous graph called the temperature spiral. It came out about 4 years ago, and it just really tells the story. This is the temperature month by month, year by year, since 1850. You can see how it was stable for a long time. You get to the 1990s, and it just explodes. And not only is it increasing, but the rate of increase, the gaps between the hottest year and the second hottest year are increasing, so that we've got an acceleration of the increase in temperatures. I'll let this go through one more time. This is the graph that keeps me up at night. And you can see we're really close to this threshold of 1.5 degrees Celsius. And I'll talk about that right now. Now, if you don't believe me, I recommend you go into some of the more authoritative publications. The 2 best sources that I've come across is the State of the Climate by the American Meteorological Society and the reports by the International Panel on Climate Change, the IPCC. And the IPCC came out with a publication 2 years ago. There was a very famous meeting called, an agreement called the Paris Accords. It was a meeting of governments and climate scientists. And they all came together to try to limit the increases in temperature, to limit the production of CO2. And their goal was to hold the increase at 2 degrees Celsius. Well, the IPCC came out with this publication saying, wait a minute, now that we're looking at this a bit more, there are a lot of really bad things that are going to happen even at 1.5 degrees Celsius. So the new recommendation by the IPCC is that we should hold the temperature increase to no more than 1.5 degrees. And as you saw from the graph, that spiral graph, we're really close. Climate scientists say that we have maybe 20 years before we will have passed the 1.5 degrees Celsius mark. And this is the very latest. This report concentrated on the cryosphere, the area, and the ocean. So the cryosphere are the areas that are frozen. So the glaciers, the permafrost, the polar ice caps. Now, maybe this is just an international, this is a problem for other people. It doesn't really bother Panama. We're just too small. It's not a problem here. Well, luckily, Panama has some of the best climate data, especially rainfall, in the entire region. The Smithsonian on Barrow, Colorado Island, which is in the middle of Lake Gatun, so completely apart from any city, any sort of source of extra heat. And we quite clearly have seen an increase of almost 2 degrees Celsius in the nighttime temperatures since 1972. And this is one of the predictions of most climate models, that the nighttime temperatures are going to increase faster than the daytime temperatures. But since the 1990s, the daytime temperatures seem to be going up, although a little bit slower during the daytime. Smithsonian has the only long-term temperature monitoring program in Panama. Panama, for reasons that are really, have never been clear, has never taken an interest in monitoring the ocean. So it's fallen to the Smithsonian to do the long-term monitoring in the oceans. And we have data of temperature in Galeta, so that's near Colon on the Caribbean side, and we've seen over 1 degree Celsius increase since 1974. Panama lacks good sea level data. There are no long-term data sets available on the Caribbean side, and there's only one tide station run by the ACP in Balboa in Panama City. And neither of that station doesn't have the international specifications that are needed. So the University of Hawaii put in a station in Porvenir. STRI put in a station in Bocas. We've got 7 years of data. 7 years is a small amount of data. You can see the amount of variation there is, but the trend through that 7 years, it says that the tide or the sea level is increasing over 7 millimeters per year. Globally, the average is something around 3 to 4 millimeters per year, and it's accelerating. 30 years ago, the increase rate was about 1 to 2 millimeters per year. The Pacific side is behaving differently. The Pacific side is showing no increase in temperature yet, and a much lower rate of increase. This isn't really surprising because different oceans have different currents. These are different parts of the oceans behave in different ways. But sooner or later, the Pacific is going to start increasing at the same rate, and the temperatures are going to increase. This just has to happen eventually. Now, consequences. The poster child for Panama is San Blas. San Blas, at least the archipelago, is going to disappear. The majority of the islands are going to disappear. The majority of the islands are less than a meter above mean sea level. The Kuna already know that they're going to lose the island. There are several islands that are already suffering from monthly flooding during monthly high tides. Sooner or later, island by island perhaps, the Kuna are going to have to migrate from the islands to the mainland. But at least they have somewhere to go. There are island nations in the Indian Ocean and the Pacific that are only islands. And these nations are going to disappear completely. People are going to lose their entire identity as a nation because these islands are simply going to go underwater. More evidence, this time from the ACP. The ACP, again, I mentioned that Panama has some of the best data. And the really best data is the rainfall from the ACP. The ACP has 140 years of high quality rainfall. And that allows us to investigate long-term trends. It'd be one thing if I said 8 out of 10 largest storms have occurred in the last 20 years, but I only have 40 years worth of data. It could have just been random. But I've got 140 years, and if 8 of the 10 largest storms have occurred in only the last 20 years, a 140-year record, that says something. That's a real flag. And in addition to these big storms, the period 2014 to 2016 were the 3 driest back-to-back years ever recorded by the ACP. So not only are we seeing bigger storms more frequently, we're also seeing more intense droughts. And this is completely in agreement with the models of climate change. It isn't proof, it isn't solid proof saying this is climate change, but it is strong evidence, and it certainly agrees with a lot of the predictions about climate change. The ACP also has their temperature data and showing the same thing. Temperatures are going up. This is from Balboa. This is an average of Balboa, Gamboa, and Gatun. So where are we going with all this? Well, it all depends on the rate of production of greenhouse gases, sensitivity of the glaciers to global warming, the ability of the oceans to sequester CO2 and the heat, as well as how that CO2 gets converted to ocean acidity, the effects of the temperature and the CO2 on forests and crops, effects of climate change on ocean currents and meteorological phenomena like El Nino, hurricanes, feedback loops. Feedback loop, for an example, would be in the areas in northern Canada, all of that tundra. When that ice melts, it releases methane. When that methane gets into the air, it causes things to heat up. When things heat up, there's more melting. That's a vicious cycle. And there are a number of these vicious cycles that we really don't have a handle on exactly how they're going to play out. Another big limitation is we simply don't know how much CO2 is going to be produced over the next 100 years, for example. So what climate scientists do is they create different models. The foremost common is zero increase. The reductions agreed to in the Paris Accords, moderate increases above those accords, and business as usual. They have these different monikers, RCP, they're representative concentration pathways. You'll see that in official publications, RCP something or other. And these are there are many different models, but they all say pretty much the same thing. Less CO2, less greenhouse gases, less the temperature increase is going to be by the end of the century. And all evidence indicates that we are on this. And this curve has actually been increased in the last few years because when they produced these most extreme scenarios, well, 5 years ago, they found out that what we were doing in the planet actually exceeded those worst case scenarios. So now the models are saying, yep, this is where we're going. Possibly 3.5, 4 degrees Celsius by the end of the century. And remember, that's just the end of the century. Everything doesn't stop at the end of the century. People have a real hard time dealing with long periods of time. So just for convenience, scientists talk about the end of the century. But that curve is going to continue as long as CO2 production continues. Most models agree with this basic scenario. The land's going to heat up more than the ocean, and the Arctic is going to heat up much more than tropical areas. Tropical areas are expected to, in worst case scenario, 3 degrees. For the Arctic, it's up to 8 degrees Celsius. And as I mentioned before, the Paris Accords were designed to limit the increase to 2 degrees Celsius. Right now, we're on track for 3.4, perhaps even more. Sea level rise is going to arrive at 1 centimeter, possibly 2 centimeters per year or even more. Right now, that 3 to 6 millimeters per year, it's hard to detect that. But when you start getting 2 centimeters per year, you can actually really appreciate that. And by the end of the century, 1 meter, some models say that in worst case scenarios, for example, some major glaciers in Antarctica or Greenland collapse, we could see 4 meters by the end of the century. And again, the melting doesn't stop here. That melting is going to continue, even if under the best of circumstances, and we stop producing CO2 today, the melting is going to continue for centuries. And that's because the CO2 in the atmosphere has a longevity that's measured in thousands of years. So unless we find a really good way of capturing that CO2 is there in terms of human society forever. So for Panama, getting close to the end now, we can expect air temperatures to increase 1.5 to 3 degrees. Sea level rises at least 1 centimeter per year, totaling to 1 meter. The oceans are going to acidify, and that's going to be really bad for things like corals, for clams, anything that produces a calcium-based structure. Ocean acidification is going to be really bad. Get ready for a world dominated by sea jellies. Changes in precipitation patterns, we've already seen it, lots of evidence for that. A significant increase in coastal erosion and flooding. You cannot raise the ocean by 1 meter without eroding the coasts. And some of the coasts here have really flat, low slopes. So 1 meter rise is going to eat back hundreds of meters in some locations. Sandblast Island's gone, composition of the forest. There's already evidence from the science in STRI that the forests have begun to change. And if you really want to lose more sleep, here's that same model extended out to the end of the century if we continue on the level with the levels of productions that we've got right now. So in 30 years, we've passed 2 degrees. By the end of the century, we may even hit up there. This is a really pessimistic model, but anywhere between 3.5 to 5 degrees Celsius is possible by the end of the century. Now they tell me I'm not supposed to leave everybody thinking, oh, the end is nigh. There is still hope. I mean, there's hope in Panama, there's hope in the world, and it's mostly because there's still lots of biodiversity. And Panama has one of the richest biodiversities in the entire world, and we still have a vast majority of the biodiversity that we ever had. There are lots of people, non-government agencies, student bodies, government, a little bit anyways. There's lots of people working really hard to try to deal with the consequences, or possible consequences of climate change, conservation in general. There are a lot of people really dedicating a lot of their time and will dedicate even more of their time in the future to help us deal with this. And even businesses have gotten into the act. Nationally, internationally, a lot of businesses know that for their bottom line, it's in their best interest to deal with climate change. And they also realize that as good partners in any society, they need to be part of that. And so there are a lot of companies that are actively donating time, resources to deal with conservation issues. So all of that is reason for hope that things aren't totally lost. Now, I'll end this talk with this image. This is a metaphor. The train is climate change, the man is us. And you can look at this in one of two ways. The one way is that the train is leaving, climate change has left the station, and we're trying desperately to catch up and do something about it. Or the other way, and this is more appropriate for certain politicians in certain countries, that climate change is coming head on and we're running straight into it thinking that there's no possible harm in what's coming. So hopefully we're going to be the first version where we're trying to catch up and deal something with it, and that the other group of people finally learn that things are flipped around and will join the rest of the world. Okay, thank you very much for your attention. If you want to get in contact with me, there's my email address. I've got a website where you can get access, especially you students, if you're doing anything about Panamanian climate, you can get all that information from my website. And if that email or that website is too complicated, just type in physical monitoring STRI in Google, and my website will always come up as the #1. Thank you very much.
Thank you so much, Steve. That was really informative. Lots to think about, especially for us living and working here in Panama. So thank you to a lot of people who've put some questions into Pigeonhole. And now my colleague Lizbeth is going to read some of the more exciting questions that we received.
Hi, thank you everybody for sending in your questions. And the first question, can you hear me? Hello? Okay, what could the impact be on the fishing industry?
The fishing industry is potentially impacted, depends on which fishing industry you're talking about, because different species operate in different ways. The El Nino phenomenon is a good example of potential problems with the fishing industry. When the El Nino phenomenon occurs, it brings in a whole bunch of warm water to the Eastern Pacific. And most fish, especially the really economically valuable fish, don't like warm water. It's too warm and it's also low in nutrients, so they go elsewhere. So as oceans gradually warm, it's expected that many fish that occupy tropical areas will begin to migrate out. Actually, not just fish, many species are expected to do that given enough time. And the corals, for example, have already been seen colonizing areas where they didn't exist before, because those areas now are much more warm enough for them. And when they die out in areas, and the corals really are almost many corals are a lost cause. Between global warming and ocean acidification, many scientists really think that the corals are going to be really beaten back. The Great Barrier Reef of Australia is almost going to completely disappear. A lot of corals in tropical areas are going to disappear because it's going to be too warm, and the ocean acidification, and we're talking about almost a 50% increase in the acidity of the oceans, are just not going to make it viable for a lot of coral species. On top of that, things like mangroves. Mangroves are going to be beaten back because in the past, when the ocean's levels increased very, very slowly, the mangroves just simply colonized farther inland. Well, the ocean's happening too fast, and increase is happening too fast, and even if they could, if you take a look at maps of Panama, right beside almost every mangrove is cattle ranching. So the mangroves don't even have anywhere to go to. So we're going to lose a lot of mangroves. And the mangroves are incredibly important areas for a lot of fish species, for shrimp during part of their life cycle. So the loss of those mangroves is going to really hit a lot of fishing industry. I could go on.
Thank you. What do you think is the best way to educate or raise awareness on climate change?
I think the best way to do it is just to keep talking about it. I'm involved in a group dealing with the mangroves. And what we learned is that it's not enough just to give a talk about mangroves. You have to give that same talk over and over and over again so that it becomes part of everybody's conversation. So that's part of why I'm giving all these talks. We've got to continue to talk about it. Everybody has to talk about it. It has to become a part of everybody's conversation so that everybody starts to do something about it.
Thank you. And I have a question here that says, why do the greenhouse gases stay in the atmosphere and not just float out into space?
They don't float into space because of gravity. That's the same reason why the oxygen in the atmosphere doesn't float off into space, because the Earth has enough gravity to hold it in. It's why Mars doesn't have an atmosphere, because it didn't have enough gravity to hold its atmosphere in. But it gets even more complicated. A lot of gases in the atmosphere get broken down by the ultraviolet radiation coming from the sun. Different gases get broken down at different rates. Methane, for example, gets broken down in a couple of years. It just so happens that CO2 is very resistant against getting broken down. So it takes a long time to break down the CO2 in the upper atmosphere.
Thank you. In regard to the current drought in Panama Canal, do you think this is caused by human activity leading to climate change, ultimately drought? Or are the droughts like these a natural occurrence?
That's a really good question, because it really gets to talk about how difficult it is to really show concrete evidence about climate change. A particular observation isn't good enough because there could be another reason for it. And it turns out that the data that we have from the Panama Canal, that 140 years, shows quite clearly that there are decadal level changes in precipitation patterns, that there are some decades that have been up to 25% drier than the last 2 decades that we've just had. And there's some evidence to indicate that we may be entering another phase of low precipitation purely for natural reason. It turns out to be linked to ocean currents that oscillate on a periodicity of decades. So it could just be that part, at very least, of these droughts that we've seen are related to this long-term natural change. On the other hand, we've seen at least 2 of these low precipitation periods, and that doesn't explain why we're seeing droughts that exceed anything seen in the past. So we've had low precipitation periods, but we haven't seen this intensity of droughts that we're seeing right now. So it's a smoking gun.
Thank you. And there is one last question. To what extent can glacier melt be halted at this point?
If we don't stop global warming, if we don't stop production of greenhouse gases, there's virtually nothing we can do. We're talking about billions and hundreds of billions of tons of ice that's being melting. It's simply the amount of energy that's involved, the amount of mass that's involved is just far beyond anything that would be either scientifically, technologically possible, and most assuredly economically possible. It's just, they're going to melt as long as the temperatures continue where they are.
Thank you.
All right. Well, thank you so much again, Steve. This has been just super informative for all of us here. Thank you for taking the time to share all your hard work with us. And I really encourage everyone to keep involved and to look for more information. So you can go to the STRI website, www.stri.si.edu. You can send Steve a message at patons@si.edu, or just type in physical monitoring STRI. So thank you everybody for attending today's webinar. And thank you all for asking questions. There were so many questions that couldn't be answered, but I will answer them in class for any of my students that are here watching. So please also, everyone, check out the rest of our Earth Week challenges and activities. They're in the Dolphin Dispatch, the daily news, and daily bulletins. Please stay safe, and have a wonderful rest of the week. Stay tuned for our next webinar, which will be on May 5th. And remember to follow our social media accounts to discover more about ISP. So one more round of applause for Steve. Thank you so much, everyone.